Hello everyone, I hope you all are doing well. Let's start our lecture today. As you already know, a lot of problems can be modeled in terms of graphs. In today's lecture and in the next couple of lectures, we will talk about graph algorithms. Some of the graph algorithms we will be talking about are graph search or traversal, topological sort or connected components, minimum spanning tree, shortest path, etc. Let's start with some basic definition. Graph is a data structure that contains two sets, a set of vertex V, a set of edges E. A vertex is also called a node. An edge is a connection between two vertices. In an undirected graph, the edge does not have any direction. You can think it as a two-way connection between two vertices. For example, the edge between two nodes or two vertices 4 and 2 can be written as 4-2 or 2-4. In a directed graph, however, the edge has directions. 4-2 and 2-4 does not mean the same edge. The two very frequently used parameters in graphs are n and m, where n is the number of vertices and m is the number of edges. In this example, the number of vertices is 8 and the number of edges is 11. Here you can see some of the real-life problems that are modeled using graph. For example, in a transportation problem, like in Google Map, street intersections can be modeled as a node in a graph, and street between two intersections can be modeled as edge. We can generate web graph from a website. Here, single web page will be modeled as node, and hyperlink between two nodes or web page can be modeled as edge. Similarly, ecological food web can be modeled as shown in the picture. To model a problem as a graph problem, we need to represent the graph in computer system. There are a couple of ways to do it. First one is adjacency matrix. In adjacency matrix representation, we create n by n matrix where A sub UB equals 1 if U and V are two nodes which has an edge in the graph. Remember, n is the number of vertices. In adjacency matrix, an edge has one entry. However, if you look at the edge 2, 4 here, we put two entries. One in row 2 column 4 and another one in row 4 column 2. Why? Because for an undirected graph, the edge 2, 4 means there is an edge between 4 and 2 also. One advantage of this approach is that if you want to find out whether there exists an edge between two vertices U and V, then it takes constant time. The problem with this approach is it takes a lot of space. Think about the case when there are a lot of vertices, however, the number of edges is very small. Also, if you want to find all the edges in this graph, you will need order of O n square time. The second approach is called adjacency list representation. In this approach, we create an array of linked lists. The size of the array is equal to the number of nodes. Each entry in the array represents one vertex, and keep a list that represents the neighbor of that vertex. A neighbor of a vertex is another vertex who has an edge between them. For example, the two vertex 2 and 4 are neighbored. That is why in the linked list that keeps tracks of the neighbor of 2 has an entry of 4. and also vice versa. Similar to the adjacency matrix representation, for undirected graph, you can also see two entries that are stored in this picture. For example, the edge 4, 2 has two entries, one for 2 and one for 4. The advantage of this approach is it saves a lot of space. The space requirement for this approach is order of n plus m, number of vertices plus number of edges. The problem with this approach, however, is if you want to find out whether there exists an edge between two vertices u and v, then it takes order of degree of u times. The degree of u means number of neighbors of u. For example, in this picture, the number of neighbor of vertex 2 is 4. 1, 3, 4 and 5, because all of them has an edge with 2. This slide lists the trade-offs between two representations. Understanding the trade-off will help you to choose the representation you want to use for a specific problem. A path in an undirected graph G is a sequence P, which consists of some nodes where each consecutive pair of nodes joined by an edge E. A path is simple if all nodes are distinct. An undirected graph is connected if for each pair of nodes u and v there exists a path between u and v. You don't have to have an edge between them, but you have to have a path between them. For example, for this graph, we can say the graph is connected as every pair of vertices in this graph has a path between them. However, if your graph extends to this whole graph here, not all the pair of vertices has path between them. For example, the vertex 10 and the vertex 1 does not have any path between them. That is why we can call this graph as an unconnected graph. A cycle is a path of length k minus 1, in which the first and the last vertex are the same. Here you can see a cycle 1, 2, 4, 5, 3, 1 with length 5. There are a couple of other cycles, but this is one of them. We know that if the edge in a graph has direction, we call that graph a directed graph. Similarly, if an edge in a graph has a weight, in that case we call it a weighted graph. You can modify your adjacency matrix and adjacency list representation to include this factor. Next, we will talk about graph traversal algorithm. First graph traversal algorithm we will be talking about is breadth first search, or BFS. The graph traversal algorithm is kind of an attempt to visit all the nodes in a graph in a systematic manner. It doesn't matter whether your graph is a directed or undirected graph. It also doesn't matter whether your graph is a weighted or unweighted graph. BFS works for all of the graph types, even if the graph is disconnected. Let's take a look at an overview of a BFS simulation. We will start the simulation from a node, in this case the node D. In the first step of a BFS algorithm, it tries to find out what are the nodes that are one path length distant from the node D. One path length distant from a node D means all the nodes that has a direct edge between that node and the node D. In our example, all the nodes that are one path length distant from D are C, E and F. At this point, we will visit all the nodes in this ripple. So BFS is kind of a ripple in a pond. First step, we find what are the nodes that are one path length distant from node D. This is kind of a first ripple. The next step, we will visit all the nodes in this ripple, C, E and F. We will visit alphabetically. Next step, we try to find out what are the nodes that are two path length distant from the node D. We also can try to find out what are the nodes that are one path length distant from the nodes C, E and F. These two will mean the same thing. In this example, we can find only one node, which is G. Next, we will visit G. In the next step, we will try to find out what are the nodes that are three path length distant from D, or two path length distant from nodes C, E, F, or one path length distant from G. The only node we find is H. We visit H and we go on. Now the question is how we are going to keep track of the nodes that are one path length distant, two path length distant, and so on. The answer is we will use the first in first out data structure called queue. So this is the BFS algorithm as a pseudocode. In this algorithm, we divided the whole algorithm into two parts. In the first part, in line 1, we mark all the vertices in the graph as unvisited because we need to visit them later. Then we will initialize an empty queue. This is the queue which will keep track of which node to visit next. In the line 3, this for loop will go through every vertex in the graph G. In the line 4, if the vertex is unvisited, then we will visit that vertex. One way to visit the vertex is we can print it out, or we can keep track of a variable inside of a node that represents a vertex, and we will keep track of the time when it was visited. The next step is we will insert that node into the queue. Then we will go to our next step of the algorithm. In the next step, while the queue is not empty, we dequeue a vertex from the queue and then look for all the adjacent or neighbors to that vertex. So all the neighbors W, for each neighbor W of the vertex V, what we will do, we will see whether the W is unvisited or not. If it is unvisited, we will visit that, or we can keep track of time when we visit that node and add that edge into a tree called T. Finally, we will add that vertex into the queue, and so on and on. Let's take a look at the walkthrough of this algorithm. At the beginning, we enqueue or insert D into the queue. Then we dequeue or remove the vertex D from the queue and visit the vertex D and enqueue all the neighbors of D. All the neighbors of D are alphabetically C, E and F. Then we dequeue or remove C and insert all the vertices that are adjacent to C. In this graph, there is none. Next, we dequeue E and add all the vertices that are adjacent to E into the queue, and also visit the vertex E. Next, we dequeue the vertex F from the queue and visit the vertex, and also insert or enqueue all the vertices that are adjacent to F but not visited. The adjacent vertex of F is C, but we already visited C, so we will not insert that into the queue again. Next, we enqueue G and visit G and also enqueue all the neighbors of G that are not visited. In this case, H. And we will go on. When the queue is empty, we know there is no vertex in the queue that we can visit from here. So we will end our algorithm to in this position. If we consider a breadth first search on a tree, what will it look like? It will look like a tree level traversal. If we start from the root A, all the one distant nodes from A are B and C. So we will visit B and C. The two distant nodes from A are D, E and F. So it will look like we are visiting all the nodes in level by level. First A, then B, C, then D, E, F, and then H, G, etc. The second graph traversal algorithm we will be talking about is depth first search or DFS. Similar to the BFS, it also systematically visits all the nodes in a graph. But the only difference here is how we visit the next node. In the BFS, we used a queue to keep track of the next node, but in this case of DFS, we will use a stack. So this is an algorithm of DFS. Similar to the BFS, it again starts with marking all the vertices unvisited. Then again a for loop which rotates through all the nodes in the V. If the vertex V we are talking about is unvisited, then we will start the second part of the DFS. What the second part of the DFS does, it marks the node as visited, then it will go through each of the adjacent node. If the adjacent node is unvisited, then we add the edge to the tree T and we recursively call the same function again from that vertex. Here is the point where it differs from a BFS. When we are done with all the nodes in the adjacency list, at the end we will mark the vertex V as finished. We can do so using a finish time array. Let's take a look at a walkthrough of that algorithm. So again we will start from a node D. We visit the node D, then we will go through all the adjacent node, but this time we will insert into a stack. So the first node adjacent to the D is C. Because we are talking about that alphabetical order, we will take C from the adjacency list. We will insert it into the stack. At this time C is visited and there is no adjacent node from C, so we are finished with C. Then we will go back to the node D. As C does not have any adjacent node, we can pop C from the stack. Next we go to the D again. At this point, not all the adjacent node of D were visited, so we will take the next node, which is E. From E, we try to find all the adjacent node of E that are not visited and push it to the stack. Only adjacent node of E is G, so we will push G into the stack. From G, we can reach two nodes, D and H, because these are the two nodes that are adjacent to G. We will not go to the D because we already visited D. Next, we will put H in the stack. Similarly, we will go through all the unvisited neighbors of H. First, we will start with A. Here, A has a unvisited neighbor B. We will go to the B. At this point, B don't have any unvisited neighbors, so you can pop B from the stack. Now we went back to A. A does not have any other unvisited neighbors, so we can take A out from the stack. Similarly, H, G and E does not have any unvisited neighbor, so we take all of them from the stack. But D has another unvisited neighbor, which is F, so we will insert that into the stack. At this time, F has only one neighbor, but that neighbor C is already visited, so we will not go to F. And F does not have any other unvisited neighbors, so we will take F from the stack. Finally, D does not have any unvisited neighbors at this point, so we will take D from the stack. Now the stack is empty, so we can finish our simulation. Here is a quiz question for this lecture. Which tree traversal is similar to DFS? How does the DFS traversal differs from a BFS? The last one, let's say you are modeling the Google map for Huntington. There are 10,000 street intersections and 100,000 streets. Next, you want to do a traversal on that graph you created. Which traversal you will use, DFS or BFS, and why? Next, we will take a look at a problem set called connectivity problem. In the connectivity problem, we see two types of problems. One is given two nodes S and T. We try to find out whether those two nodes are connected or not. Another type of problem we will see is the shortest path problem. Given two nodes S and T, we try to find out what is the length of the shortest path between S and T. One related definition of our problems of connectivity is called the connected component. So what is the definition of a connected component? Connected component of a graph consists of all the vertices that are connected to each other. In this example, we have a graph with 13 vertices and 3 connected components. The connected component containing the node 1 is 1, 2, 3, 4, 5, 6 and 7. The connected component containing the node 10 is 9, 10. If you have ever used any photo editing application like Photoshop or even Paint, you have used this algorithm, maybe knowingly or maybe unknowingly. This algorithm is called the flood fill. You select some area and you want to fill that area with different color. For example, given a lime green pixel in an image, you want to change the color of entire selection of the neighborhood lime pixel to the blue. What you can do here, you can use the DFS or BFS to do that, and this is what is being done in all of those photo editing applications. In that algorithm, what you do, you start from that pixel and start painting all the neighboring pixel when the neighboring pixel has green, and you will stop your recoloring when you cannot find any neighboring pixel that has green color, and then you will end up recoloring all the green colors pixel into blue pixels. Let's take a look at how we can find out the connected component of a graph. Let's say you start from a node S and you want to find all the nodes that are reachable from S. You will start with a set called R. Initially, R will contain only S because you have not done anything at this point. Next, what you will do, you will grow R and add more and more vertex. The way you will add more and more vertex, you will consider all the nodes in S and try to find any node V that are not in R, but there is an edge from U to V. If you have included all the nodes, searching through all the edges, you will end up a region or component which all are connected, but there are no other nodes that are connected to that component which does not lies in R.